So if you work with real engineering data, the data logger output from a manufacturing process or an instrument, such as particle size measurements, sensor readings from a thermocouple, you already know the issue. The data is never clean when it arrives. There's missing values, duplicate rows, timestamps in the wrong format. There could be sensor dropouts in your data sheet. They look like zeros, but they're actually errors. Timestamps can sometimes get mixed up. So before you analyze anything, before you can spot any trends or identify failure modes or make process decisions, you have to clean your data. So in this video, I'm going to walk you through exactly how to do that in Python using Pandas with two real engineering examples: a data logger output from a manufacturing process, and then particle size data from a lab instrument. So my name is Dr. Colleen Spiegel. I'm a chemical and electrical engineer, educator, author. This is Python for scientists and engineers. So let me start with why this matters, because I want to make sure that we're on the same page about what is actually at stake with your data. In engineering and science, decisions based on data have real consequences. A process optimization decision based on dirty data can reduce yield, and a quality control decision based on data with undetected outliers can let a defective product through. A failure analysis based on data with missing timestamps can lead you to an incorrect root cause in your data. So I've worked with data logger outputs from manufacturing processes that contain sensor dropout events, periods where the sensor stopped reading and logging zeros instead of actual measurements. If you calculate the average process temperature, including those zeros, but you'll get a number that's meaningless and at best could be misleading at worst. So I've also worked with particle size data downloaded from lab instruments that contain header rows, units mixed into data columns, and duplicate measurements. Every one of those issues have to be identified and resolved before you can analyze that data. So this is not glamorous work, this part, but it's work that determines whether your analysis is trustworthy. So let's do this systematically in Python. So we have the data logger output from a manufacturing process. This is the kind of data that comes off of a data acquisition system or a SCADA system, and it's often exported as a CSV file. It looks clean when you first open it in Excel, but Python will show you what's actually there. And the old method of doing this is manually cleaning the data in Excel or graphing it and identifying, that it doesn't look right. But sometimes a value can slip through or something can slip through, and this will skew your data analysis. So we're going to create a simulated data set. This is a realistic version of what you might pull from a process data logger. So we're going to import the Pandas and NumPy library as PD and MP. We're going to generate realistic engineering data. So we have some timestamps that we're going to put in, our temperature data. We're going to drop in, of course, some zero data, an instrument error code. We're going to put in some pressure data. We're going to put in the initials of the operators that might be running the process. And then we're going to place that into a data frame and then print it so we could just see what it looks like. So the first thing you want to do with a new data set is understand its structure and identify any problems before you start your data analysis. So to understand our data set, we're going to print the shape, our rows and columns of our matrix, basically. We're going to look at the data types of each column in our matrix, and we're going to look at a summary including null counts in our matrix. And then the describe function will be used to generate a statistical summary, which is a great built-in function. So when we look at our data, we notice a few things right away. The timestamp column is a dtype object. So this was loaded as a string, not a datetime object. And the temperature column has a 0, obviously, and 999. So these are clearly not real process temperatures. The pressure column has a missing value. There's a duplicate row, and there's white space in the operator column. So let's go ahead and fix each one of these issues systematically. So the first thing we're going to do is convert the timestamp to datetime. So we could do this using a pandas function to datetime. We'll print our data types to take a look at our new data types, and you'll see that our timestamp is now date times 64. So we could do time-based operations with this matrix column. So this is one of the most common data type issues in engineering data. The timestamps loaded as strings cannot be sorted, sliced, or used in time series calculations. So always convert those. So the next thing we're going to do is identify and remove duplicate rows. So we'll check for duplicates using our duplicated function. Then we're going to print our number of duplicated rows to view those. So we see those, we're going to remove the duplicates, but keep the first occurrence. So we're going to use the function drop underscore duplicates, and then we're going to look at the shape after removing the duplicates. So sometimes duplicates occur in process data from system restarts or data export overlaps. So always check these before continuing on with analyzing your data. So the next fix we're going to do on our data set is handling sensor dropouts and error codes. So this is the most important step for process data. Zero values and instrument error codes are not real measurements, but Python doesn't know that, right? You have to tell it. So we're going to replace our sensor dropout zeros with NaNs, not a number, because in this process, we know the temperature cannot be below 50 degrees Celsius. So we're going to use the replace function, 0 with not a number. And then we're going to replace the instrument error codes with not a number as well. So we could also replace any physically impossible values. So for example, if our temperature is less than 50, we're going to replace it with not a number. Or if our temperature is greater than 200, we're going to replace those values with not a number as well. So we're going to print our temperatures to take a look at that. So to go through these values, I'm using my process knowledge here, obviously. I know that temperatures below 50 degrees Celsius and above 200 degrees Celsius are not physically possible in this process. So that domain knowledge is what makes engineering data cleaning different than generic data science. So you know what the data should look like. Use that knowledge to clean your data set. So the next fix we'll do is handling missing values. So we're going to check for any missing values by column. So we're going to use the function isNull.sum. And then if we find any, we're going to drop the rows with any missing values. So we're going to use the function dropNA. We could carry the last known value forward, which is good for sensor data that change very slowly. So we're going to do the fillNA method, ffill. And then we could also interpolate, estimate from surrounding values. So if we have values at a certain time before and after, we could probably safely estimate what that value should be. So we're going to use an interpolate function with the method of a linear interpolation. So we're going to do that for both our temperature and pressure columns. So the approach that you choose depends on your process. If you have a slow changing physical parameter like temperature in a controlled process, interpolation is a reasonable approach. But if it's obviously a rapidly fluctuating process temperature or something like that, something like a forward fill might be better. Dropping the row entirely might be the right choice also, depending on your data set. So the next fix we're going to do is we're going to clean our string columns. So we're going to strip the white space from our string columns. We're going to use this function str strip. We're going to convert to uppercase just for data consistency. So for our operator column, we're going to do str upper. And then our next fix we're going to work on is handling our missing timestamps. So if the timestamp itself is missing, we're going to drop that row because we just don't know what time that data came in. So we're going to use dropNA function, and we're going to look at the timestamp column, and then we're going to look at the shape of our matrix. So if we want to verify that our data set is clean, we're going to do a final check. We can use the functions info, describe, and isNull and sum, and we'll print those functions to determine whether our data set is clean. So every timestamp has a proper timeline. Every sensor value has physically reasonable bounds. Missing values have been interpolated. Duplicates have been removed. The string columns look consistent. So now we have a data set we can actually analyze. We're going to look at another data set, particle size data from a lab instrument. So this is a slightly different problem. The instrument output files often have header rows. They have metadata mixed into the data, inconsistent column names, and units embedded in the values themselves. So I'll show you what this looks like and how to handle this. So to do this exercise, we're going to simulate particle size data that might come from an instrument. So we're going to have issues with the header rows, mixed units. We're going to have inconsistent naming. So here's our raw data. Our header rows are PS-001 through PS-006. We have particle diameters. We have some that have none. We have the units embedded in some of these. We have column names. Some of them have column names, some of them don't. We're going to also put in some inconsistent capitalization. So then we're going to look at our data set that we created using the print function. So to clean this data set up, the first thing we'll do is we'll actually remove the header rows because this is not actual data. This is just metadata. So we're going to look to see what the string contains. So we're going to use this str.contains function and print. We're going to standardize the column names next. So we'll rename the columns for consistency. So we have the rename function. The column's going to be D50, D90. We want to make the capitalization consistent in those also. And to convert all the column names to uppercase, we're going to use columns.stringUpper, str.upper. We'll print the columns to take a look at what they look like. The next part we'll do is remove units from the values and convert these to floats. So this is a common issue with instrument data. The unit label is embedded in the numeric value as a string. So from the particle size columns, we have the microns, abbreviated UM. We're going to convert that to float, and we're going to do that using the str.replace function. So we're going to look at our new data, what it looks like, using the print function. Our next way we're going to clean this data is to remove the duplicates. So this is very common with these instruments if they encounter a power surge or a blip. We're going to look at the shape first of the matrix, and then we're going to use the function drop_duplicates, and then using the shape again to make sure that the function did its job. So our next fix will be handling the missing values. So we're going to print using the function isNull.sum. We're going to look to see what's missing, and then we can drop the rows with a missing sample ID because they cannot be identified. So we're going to use the function dropNA. For missing span values, we can calculate this from our particle size data, our D10, D50, D90 particle sizes. So we do a calculation, and we're going to fill using fillNA. And we're going to print to take a look at what our data looks like now. So this is what I did with the span calculation. I used my domain knowledge of particle size analysis to calculate the missing value from the data that was already there. Span is a derived parameter. If you already have the D10 particle sizes, D50, and D90 particle sizes, I can calculate the span rather than losing that row entirely if you want to keep that row for some reason. So this is where your domain expertise comes in when you're cleaning the data set. If you didn't have any process knowledge, somebody that just knew Python or was a data science but didn't have process knowledge would just automatically drop that row. But obviously, if you have process knowledge, you can understand whether to keep that data, how to use it, and what to calculate with it. So we're going to do a final check on both of these data sets. So we're going to print with the manufacturing process data. We're going to look at the info function and the describe function to have a summary. And then we're going to do the same thing with the particle size data. So why does clean data matter? So I'll show you why all of this work matters by running a quick analysis on the clean data and showing you what you would have gotten with the dirty data. So in Python, we're going to import matplotlib.pyplot for plotting, which makes beautiful, beautiful plots. So we'll plot the clean process temperature data, and then on the axes, we'll put the timestamp and the temperature. So in the code, you could see that we're putting in our labels and our parameters on the graph. And then we're also going to plot what the dirty data would have shown. So we're going to put our axes and also, the colors of the lines and so forth on the graph. So we're going to make it look good. And then we're going to use the show function to show the graph. And along with the graphs, we're going to also compare the statistics. So We're going to look at the mean of the dirty temp and also the clean data. We could take a look at the difference. The clean data shows a stable process running at about 82.5 degrees Celsius, which is what you would expect. But the dirty data gives you a mean that's meaningless. The data is skewed by the sensor dropout zeros and up by the error code that we had. So if you made a process decision based on dirty data, you would be making it on numbers that actually don't reflect reality, which is why data cleaning is not optional. It's the foundation that every data analysis or every model that you create and every decision is built on. So this is essential for your data before your analysis. So in this video, we covered the complete data cleaning workflow for two real engineering data types, a process data logger and lab instrument data. And the key steps that we covered include converting the data types, especially timestamps. We removed the duplicates. We handled dropout data and error codes using our engineering domain knowledge. We handled the missing values. We cleaned the string columns. We removed the header rows from the files, and we removed the units embedded in the numeric values. When it was needed, we used our domain knowledge to calculate the missing derived parameters. So every one of these techniques came up because of something, and I've actually encountered these exact scenarios with real engineering and manufacturing data. So these are not textbook examples. They are problems that you'll actually face. So subscribe to my channel for more Python for scientists and engineers. I'll post practical Python techniques for real engineering and scientific data problems every week. My name is Dr. Colleen Spiegel, and I'll see you in the next video.